And now we have Danielle, our Best Thesis awardee for 2021. Danielle, oh yes.
Better? Better. Day 2 folder.
So while Danielle is preparing, our thesis is Domain Adaptation for Neuro-Machine Translation. It was conducted on the University of Cambridge. Our supervisor is Bill Byrne. And at the same panel awarded Danielle her best thesis. So Danielle, the floor is yours.
Okay, excellent. Good morning. Thank you for sticking around. This will be an extremely high-level overview of my thesis on domain adaptation for neural machine translation. So, as you probably all know, if we have an empty system today and we have enough training data, we can get pretty good performance on unseen sentences, assuming those unseen sentences have some kind of domain overlap with training data. And a domain can mean many different things. It usually comes down to some kind of vocabulary distribution. But there's always going to be new domains. And the traditional example is you have a news domain model and you're interested in a different domain, so you adapt. But there are other cases that might be new language appearing. It might be that there's language that already existed, but maybe you didn't care about it so much before, and you do now. For example, news domain systems in the last couple of years suddenly having to contend with a lot of biomedical vocabulary. And when you have this new domain, you might be able to get some new training data for it. But typically, that's far less data than you had for the original model. Do I need to move this further from my mouth? Any better? Excellent. So this is a case where you really want to adapt your model. You can retrain on everything. That often works. But it's inefficient. It takes time. It takes energy. And then when you have another new domain, you just have to do it all again. So domain adaptation. There are a lot of ways to do it. I don't claim to cover nearly all of them in the thesis, but what I do is take 3 different axes to domain adaptation. The first, what I call data-centric, is exploring the different ways you can show data to the model, so a different order of domains. The other is tuning. So actually changing the algorithm that you use to adapt a model. And then the third is a slightly different approach. If you assume that you have maybe a generic model and a domain-specific model, at inference time, how should you translate a new unseen sentence? And then my thesis finishes with 2 case studies kind of taking a domain adaptation framing to other areas of research. And in the interest of time, I'll just talk about the second one today, which is how I used a domain adaptation framing to improve gender translation. So I start off with this brief exploration of data curricula in the context of the WMT biomedical task. The nice thing about the biomedical task is we know approximately the topic and genre of the data that we're hoping to translate. And we have several different domain data sets that are very similar but also distinct. And that's a nice setting to explore variations on simple transfer learning. So the traditional way to do domain adaptation is you have one pre-trained model, one new domain, you transfer from the pre-training domain A to the new domain B. And I explore a couple variations on that. The point of this section is not to show astonishing new results, although there are a couple of interesting outcomes, but it's actually to highlight 2 problems with this kind of approach. Problems being forgetting and overfitting. So first, iterative transfer learning. If we have this target domain health, relatively small, not tiny, but relatively small, and we want to get a good model on that domain by transfer learning from another larger domain, in this case all biomed, we can do that. We see that the traditional domain adaptation cases here, if you train just on the small domain, does okay. You get a boost from pre-training on a larger domain. What's interesting is that you can actually also boost the larger domain by pre-training on the small domain. If you train on health and then back to the large data set and then finally train on health again, that performs a little bit better. So that's a kind of simple data curriculum. What's interesting is when you look at what happens to the larger domain, and this is a case where these are very, very similar domains. Health is actually a subset of all biomed. We still see this boost, the comparison from training only on all biomed versus pre-training on another domain, even if it's smaller. But when you tune away from that domain, you see some forgetting. Not very much. These are very related domains. But a little bit of forgetting even in this kind of almost ideal case. So this is the forgetting problem. And this is very brief tuning, very similar domains. If you have very different domains, this problem becomes a lot more severe. The other thing we tried in a following year was specialization. So this is a different kind of curricula where you slowly remove the less relevant data from the training set and you focus in on this highly specific data set that you're interested in. In this case, Medline abstracts. This is a few tens of thousands data set, very good match for the data we want to translate. The difficulty is you get to a very, as you get to a very small domain, is the impact of any noisy sentence pairs becomes huge. In fact, again, Medline is a subset of all biomed. The all biomed domain did not have a problem with sentences like this which have an abstract title in them. Another thing about Medline abstracts is the English side often has a title in square brackets. The non-English side does not. When you fine-tune on a set of sentences like this, suddenly the model gets confused and starts hallucinating whenever it sees text in square brackets. Now, you can filter out these sentences. It's tricky because the source and the target are often quite fluent, and there's often quite a lot of language overlap between them. So these are not completely bad translations, but they're just problematic enough to cause issues in the translation. The other problem with filtering them out is that these can often provide useful vocabulary examples. You know, sometimes you might want to tune on specific language which is only in this set of non-perfectly aligned examples. So, if possible, we don't want to filter them. But it causes this overfitting problem if we do tune on them simply. So what can we do about that? In the next part of my thesis, I explored two possibilities, given an adaptation set and a curriculum. Brief interlude. Okay. Excellent. Given an adaptation set and a curriculum, how can you adapt? Or how should you adapt? And two alternatives that I explored: regularized tuning to avoid the forgetting problem, and a minimum risk training to avoid the overfitting problem. So regularized training, specifically in this case, elastic weight consolidation. It was proposed originally for computer vision. We applied it to translation, not just from one domain to another, but actually sequentially across more than one domain. The idea is that you regularize the training objective, but interestingly, you do so differently for each parameter. You aim to regularize the parameters more if they were important for this pre-training task, PT. So you can see from the plots going sequentially across domains, you see more and more forgetting if you regularize. The problem is improved somewhat. What it's harder to see from these plots is that if the domains are actually related, you can actually get better convergence if you regularize than if you don't. Possibly that forgetting is taking away behavior in the previous domain which would have been useful in the new domain. Minimum risk training. It's an alternative to maximum likelihood training, which often gets used during fine-tuning of a model. The idea of maximum likelihood is that you train for max likelihood on reference sentences. The idea of minimum risk training is that you minimize a metric-based risk over model samples. You don't throw away the reference, you use it in the metric, but if there is a problem with reference sentences, like in the overfitting example I gave, it allows you to rely more on the model distribution. We actually developed a variation on minimum risk training that puts the model samples in the context of other similar model samples. We found this was more sample efficient. And to summarize the various approaches that we took for this medline tuning overfitting case, we found that minimum risk training as a final step did give slightly higher scores. It is robust to this misalignment problem. I've written no knowledge of misalignments needed because this was work done before very good neural filterers. But you don't have to know what the problems in the data are necessarily. You can go ahead and rely on the model samples if your model is sufficiently converged. I'm now going to change tack a little bit. Let's say that you have, in this example, two domain models, a news domain, a biomed domain. You have an unseen sentence as input, and you might want to know which model would be best to translate it. Or if you have the compute time and you want to use an ensemble, how would you weight that ensemble? What interpolation would you use across the models? In this paper, we took an extremely simple weighting approach. We used an n-gram language model, very lightweight, on the source sentence. The language models were trained on the training data for each domain model. And we simply got a score from the different domain language models. And we found those are quite intuitive, so we've got some examples here. These are all sentences that come from a development set that is labeled as the biomedical domain. But you can see from the weights and just from looking at the vocabulary, some of them have a kind of conversational style. Some of them seem like maybe they're IT sentences. Those are quite well handled by a generic model. And then some have the biomedical specific terminology. So we found these interpolation weights from our n-gram language models, and we compared the scores, if we used that weight for each on a per sentence basis, to a kind of grid search interpolation weight between, this time, a biomedical model and a health model. These are very similar domains, but even in this case, the best weighting isn't necessarily intuitive. For the health dataset, the best thing to do was always use the health model. Fair enough. For the biomedical sciences dataset, which is a subtly different domain, the best thing to do was actually a kind of midway weighting between the two. But if you just use the simple heuristic on a per sentence basis, you actually outperformed anything we found during grid search. The next stage on is, okay, we've said that we can have an interpolation weight on a per sentence basis. Well, what if we have, say, a long sentence, and the domain of that sentence changes during? You know, if you imagine long context translation, if you're translating multiple sentences in a row, that's very possible. So we extended Bayesian language model interpolation, which was as the name suggests, originally intended for language models. We extended it to condition on a source sentence and a partial translation history. And that allows weights to vary during the inference process. And again, somewhat intuitively, the weights change depending on the sentence. What's immediately striking, if we do this over 3 quite different domains, is uniform ensembling in red is not a good idea if the domains are at all different. But the per sentence ensembling methods can actually outperform the oracle case where you just pick the model that matches the data. Okay, changing tack. This is a case study on various methods I've talked about as applied to gender translation. And we already heard today and yesterday, MT struggles with human referent grammatical gender. There's some indication that that's related to the distribution of human gendered terms in the training data. But either way, it's a vocabulary distribution related behavior. That got me thinking. It's like a vocabulary, that's like a domain. Can we try domain adaptation techniques? Yes. I tried 2 different training set creation methods, both synthetic to different degrees. The first, we just gender swapped with some heuristic rules, some English training sentences, forward translated them into a target language, tuned on those. That's about 100,000 lines, took a few hours to tune. The other is that I made a template, filled it with some gendered terms, and forward translated that. It's very short, I could check it manually. Tuned on that, that took about a minute. And what I call the handcrafted, the fully synthetic set, vastly outperformed tuning on that kind of counterfactual semi-synthetic set. In fact, the forward translated set, in some cases, made things worse, possibly because it was lacking filtering. What's interesting, though, is if you look at the right-hand plot, that is a plot of blue score, and you'll notice, particularly for English-German, the blue score drops dramatically for the handcrafted set. This is the forgetting problem that I talked about to start with. But we have techniques to deal with forgetting. So we tried 2 of them, elastic weight consolidation and constrained rescoring. Elastic weight consolidation I've already mentioned. Constrained rescoring takes some inspiration from the ensembling part of my talk, where we had this intuition that actually certain parts of the sentence might benefit from one domain, certain parts might benefit from another domain. We don't need the gender-sensitive model to translate every word in this sentence. We just want it to change the human gendered words. So if we create a translation with our original model, which may have bias, we define some different gendered options in the target language, which just needs a morphological analyzer, and then rescore with our gender-sensitive model, but only allowing it to change certain words, we can get much better gendered translations. There is still a little bit of a trade-off in accuracy and in blue, but far less so than before. And another advantage of a rescoring approach is that you can actually get those initial translations from anywhere. We applied this to the outputs of black box models, which these were provided a few years ago. I'm sure they're out of date. But we rescored these, and we were also able to improve the gender translation accuracy. This is for percentage accuracy on a EAMT set for all of these systems. One final point about framing gender translation as a domain adaptation problem. Gendered terms of address for humans are not static. New ones are appearing all the time. In English, we have singular neutral pronoun they, which gets used quite frequently and has done for a while. For other languages, new terms are being proposed, new terms are being developed. And a reason that often gets used in the MT literature for not working on this stuff is there's no consensus. What we tried doing was taking a template approach to this kind of new gendered vocabulary in a richly gendered language, using things like pronouns in different cases in a template approach, with the idea being that if a specific user has specific pronoun requirements, that can be a use option later. And we showed that you can actually do this using the same kind of synthetic adaptation set. You can encourage a model that had previously not seen anything like this to produce this kind of vocabulary in appropriate places. So, there will always be new domains for MT. There are a lot of ways to address those in this thesis. I talk about just a few of them: data, curricula, adaptation scheme, ways to combine at inference time. But maybe more importantly, I hope I've said that if there's a problem that has this kind of vocabulary-related issue that maybe could benefit from two different kinds or more of MT behavior, you might want to try domain adaptation techniques, even if you wouldn't normally think of that problem as a domain adaptation problem. I've got to end by thanking my supervisor, Bill Byrne, all of my collaborators, RWS Language Weaver, who I now work for, funding body EPSRC, and of course, EAMT for inviting me here today. Thank you very much.
Thank you, Danielle. Questions?
Okay.
Hello, thank you very much for a very interesting talk. I had a question about forgetting. In the first part of your presentation, you mentioned that you were using the elastic weight consolidation. Have you compared this approach to data mixing with oversampling and how it corresponds to forgetting?
So data mixing as in taking some data from the generic domain and mixing that in. Kind of.
And also oversampling the in-domain data, so that the model sees the in-domain data more frequently, and then but you take more of the generic data.
Yeah. So mixing in the generic data, it's something we tried a little for the biomedical domains, and it helped a little bit because, as I said, they had some overlap. I know that recently there's been work which does combine elastic weight consolidation and data mixing, and they found that it works quite well. We found that it kind of depends on the domain. If they're very similar, it kind of just pollutes the target domain. If they're quite different, yeah, it can help quite a lot. But they're trying to do quite similar things.
More questions? You have one more.
I also have a question regarding the ensembling of the models. In the second part of the presentation, I think you have shown a static approach and more dynamic, right? So if, for example, in my case, I think the dynamic approach would entail a lot of implementation. How would you recommend implementing the static approach? Is there like some sort of percentage that you can average the generic and the in-domain model? Or this is very empirical?
So the static approach, okay, so the way we had ensembling implemented is that you have some predictions from one model, you have some predictions from another model, and you combine them in some proportion. And that proportion is the bit that is the ensembling weight. Now, how you get that ensembling weight is the bit that varies between the methods. A uniform ensemble, which is the typical method, just basically multiplies them both by 0.5, or equivalent in log scale. A static approach would, for each sentence, load in a different pair of weights, 0.9, 0.1, 0.6, 0.4, and so on, and multiply by those weights on a per sentence basis. So in the framework we were using, this was no more implementation hungry than just a uniform ensembling approach. The more dynamic approach actually is also not much more heavy than that, because the only thing that differs is how you calculate those weights. Effectively, you recalculate the weights at every step depending on the last score from the model. So it's just a slight change in how you find those interpolation weights that are used to combine the model predictions in ensemble.
Okay, thank you.
More questions? I have one, Danielle.
Mm-hmm.
How fast, with all you have learned, how fast are we from creating an empty domain adapted model?
How
How fast in time?
It depends on how much how much
An
you want to
estimate.
do.
Do you have an estimate with all the techniques you develop of how fast you can create an empty domain adapted model these days?
So are you saying if you have a model and you want to adapt it? It depends how much data you're adapting to. The gender handcrafted experiments I did took about a minute. Some of the experiments took hours, but yeah, a minute. It was 400 sentences. I iterated over them twice. It worked very well. But some of these domains, if you have a lot of very varied data, yeah, that can take hours if you want good performance, and if, as the question said, you want to mix in some generic data, or if you want to do some fancy tuning algorithm to avoid forgetting, that can take longer. It depends on the use case, which I realize is not helpful.
Thank you. More questions? Yeah. Oh, yeah.
Yeah.
We will go back to you again.
I was wondering, what do you generally look at most when you're performing domain adaptation as your stopping criteria? Do you use purely domain data, a mix of domain and original?
So ideally, if you have it, you would use, I think you would use validation data from both the target domain and the generic domain, assuming you care about performance on the generic domain. You might run into issues. In some cases, you might want to adapt a model where you don't have access to that data. So in that case, you kind of have to look at the performance on the in-domain development set and hope that you're not going too far. That's a case where stuff like elastic weight consolidation can really come in helpful, because at that point you know that you're probably not going too far from optimal on the generic domain.
Here.
We adapt a few hundred models a year for domain, and one of the common problems that we have is that after the model is domain adapted, linguists use it to translate and post-edit, and they report different types of errors, right? So this is a recurrent error, this is a recurrent error, they use it for 6 months, a year, and then some patterns arise. From your research, are there any tools which can help engineers pinpoint those problems in the output from the feedback and create small data sets to fix them? So optimizing the model continuously after it has been adapted for the domain, and then making it better and better, nurture it over time. What would be the tool to industrialize this?
Yeah, it's a very good question. This is not something I dealt with in my thesis, but it is something I've thought about. I think it basically comes down to synthesizing data. So this is what I touched on in the last part with this gendered set. If you have some idea of the problems in your model output and you can pinpoint those down to the vocabulary, if you can produce some data that addresses that vocabulary and you can do it so that the data is natural seeming, or mix in some generic data, or use something like elastic weight consolidation, then that is how I would probably go about it.
This approach is like very manual. Is there a way to do it on an industrial scale? Sorry.
So the question is, is there a way to scale that up, basically? I mean, if you have customer complaints or specific complaints, that is already kind of manual, that there are particular problems that are being flagged. But you can synthesize data on a larger scale for, at least for higher resource language pairs. If you have a decent morphological analyzer, you can figure out how to slot the data that you care about into sentences that you have.
I think there was a very hard question, and you need a proper coffee to answer that. So it's a great, great pleasure. I know there are more questions, but maybe you can take the opportunity at the coffee break to talk to Danielle and Mattia about their thesis. It's with a great, great pleasure to deliver you your award, Danielle. Well done.
Thank you very much.